In this talk, I'll discuss how to make AI models efficient and reliable for deployment in healthcare under real-world constraints. Let me briefly talk about why this problem matters. Healthcare is fundamentally about human lives. It is part of every stage of our life, from prenatal care to later life care. In reality, no one can opt out of healthcare. Because of that, decisions in healthcare directly affect human lives and well-being, which make this a uniquely high impact and high stakes domain. A large fraction of these high stake decisions is driven by medical imaging data, as already discussed by other panelists as well. Therefore, medical imaging sits at the core of modern healthcare, and it spans many modalities from MRI and CT to X-ray, ultrasound, endoscopy, and pathology. Clinicians use images of these modalities to detect disease, guide treatment, and monitor patient over time. The challenge is that the volume and complexity of medical imaging data is growing faster than human capacity of processing this large-scale data manually, which make the human-only healthcare system very difficult to scale with the growing demand. This is exactly where AI can help. AI can help in different ways. Let me talk about a few. First, AI can assist in diagnosis. It can be used for preventive care and risk stratification, longitudinal patient data analysis or integration over time easier, and also very complex procedures like surgery. Importantly, this capability spans across the human life cycle, from early detection and prevention to long-term care and even in the death stage. The real challenge is scaling these capabilities across hospitals, patient populations, and over time. So what makes it still challenging to scale AI in healthcare? There are several practical barriers for this. First, most existing models are compute and memory heavy, which struggles to deploy in resource-constrained setups in real-world healthcare. For example, hospitals in underdeveloped country or point-of-care setups or real-time systems where we need, for example, physical AI as discussed in the last presentation. So we need AI models. Those are real-time. And we need the models being compute and memory efficient. Secondly, limited and expensive level data. And in case of segmentation or pixel level classification task, this is more challenging to get pixel level annotation of images because experts are usually busy. So annotating larger scale images are expensive and also very much difficult. Third, many important clinical cases are rare and hard cases. And fourth, distribution shift is very common in healthcare domain. The model trained on data from one hospital, and if we try to deploy in another hospital, its performance degrade because data distribution changes due to protocol changes, patient population changes, and changes in over time. So these challenges defines the gap between the lab scale AI to real world healthcare deployment. And my research addressed these challenges by building AI models that remain reliably deployable when compute is limited, data is scarce, and environment change. The goal is to build model that not only work in cloud scale resources like large scale GPU access, but also work across different deployment scenarios, including hospitals in underdeveloped country, rural clinics, bedside systems, emergency medical services, or mobile devices. The goal is to make the AI not only great in healthcare, but also good for all in different places. So to address the fundamental challenges I discussed, I contributed in two different angles. First, I developed compute and memory efficient architectures to make models efficient so that we can deploy them in real world hardware. And I work on data efficiency and reliability to address the data scarcity challenge and also making them reliable across different hospitals or sites. So in this talk, I will discuss two complementary work in this direction to show you how can we make them both efficient and reliable. So I will start with our work MCAT, that is a new compute efficient architecture that we developed, and it can reduce the computational cost by around 80% for medical image segmentation without sacrificing accuracy. Rather, it's improved the accuracy of segmentation. So let me briefly talk about the segmentation itself. So medical image segmentation is a dense prediction task. It assigns a class level for each pixel, so that can be organs, lesions, tumors, vessels, different kind of medical biomarkers in an image. So if you see the right image here different organs are labeled manually, and our goal is to segment this organ using AI methods. And this is a critical step in disease diagnosis, treatment planning, and monitoring patient outcome over time. So the commonly used architecture for segmentation is U-shaped architecture. So where we use an encoder that extract high-level information from the image gradually, that means the latent information, and then we send those information to a decoder that reconstruct the high-resolution segmentation of the image with the help of skip connections. Now, I would like to share an important observation here. Encoder is highly optimized in computer vision domain because this is part of many different kind of tasks. However, decoder remains the primary bottleneck. And so in this part, I'll show what makes the decoder primary bottleneck. So there are several fundamental causes that make the decoder primary bottlenecks. First, most blocks or building blocks used inside the decoder, they are compute or memory heavy because those are not optimized properly and repeatedly used inside the decoding phase, and we need to process high resolution feature. And second, the reconstruction operation is expensive and it is built on convolutions as well. And third, in most U-shaped architectures, skip features are concatenated with the decoded features, that leading to more computations. Now, when we try to see whether we can actually reduce the computational cost naively without affecting accuracy, we have seen that it significantly drops the performance as well if we reduce or scale down the decoder itself half of the compute requirements. This suggests that naive scaling is not working. We need something that is optimized. The big question is, how can we optimize the decoder? So we can optimize the decoder by redesigning the fundamental operations. Those are heavy compute, but are not properly optimized. So I will now I'll show how can you optimize the convolutional operation, that is commonly used operation in different kind of architectures or deep learning architectures nowadays for computer vision tasks for efficiency. So I will start with standard convolution that is commonly used in computer vision domain inside different kind of architecture. So which applies convolution across different feature maps together. So that means the multiplication by the filter together, leading to more computational cost. However, it can capture rich context. So now we are talking about making them efficient. So there are already some efforts. So that tries to reduce the computational cost of the standard convolution. And this is called depth-wise separable convolution, which applies the convolutional filter for each feature map separately. And in this way, we can reduce the computational requirements significantly, but it struggles to capture context across different feature maps, so leading to poor context capture. Now we ask a question, can we further improve this depth-wise separable convolution so that it can capture better context while improving the while reducing the computational cost further? Yes, we can do that. We introduce a new convolutional operation, that is multi-scale depth-wise convolution, where we strategically use the depth-wise convolution for efficiency. We are not using the full depth-wise separable convolution, but only the depth-wise convolution part. But we apply them in multiple kernels to capture multi-level or multi-scale context from the image. This is very much essential because where in an image we have both smaller and larger context, or both local and global context. So if we use different kind of kernels or receptive field to capture those, that actually helping to capture better features. And then we aggregate them using addition and then apply a channel shuffle operation that makes the picture maps together and capturing the cross picture map information. By this way, we have our new block that is further optimized for efficiency while being more representative for the feature extraction. So if we see the complete requirement for these different blocks, we can see that standard convolutions require polynomial compute requirement with respect to C. Same for depth-wise separable convolution, because this uses the point-wise convolution here, that actually increasing the cost here as well. So this C can be even more than thousands of picture maps in the input layer. So that's why if we see ours, as we are using just only depth-wise convolution that is linear to number of picture maps, and it actually reduces the compute significantly. And if we just use C equal 128, we can see that this computation actually brings down 65 times from the standard convolutions computational requirement, while it can also reduce 4 times compared to depth-wise separable convolutions. By this way, we come up with a new operation that is highly optimized for efficiency, while it can capture rich context using multi-scale context capture. So now I'll show how can we translate this specific convolutional operation to a end-to-end architecture, deep learning architecture that can actually do the medical image segmentation. So based on this, we introduce a new decoding architecture that is convolutional based, efficient multi-scale convolutional attention decoding. The reason behind this is, in case of decoding, we need to capture the local information, pixel level information more instead of global information. So that's why we built our decoder based on convolutions. But we use existing transformer based encoder. So we need the transformer based encoder to capture global context from the image, and it is proven to transformers are performing better than CNNs nowadays. So we use pre-trained transformer image in the dataset, and then we redefine the decoder using our newly defined convolutional operation. And this is our new decoder. We call it MCAT decoder. And we've here made 3 fundamental contributions. First, we introduced multi-scale convolutional attention module to replace the refinement operation. And then we introduced efficient up convolution block. And also we introduce a gating mechanism, that is large kernel good attention gate, to bring only relevant information from the encoder to the decoder. Now we evaluated these methods across different kind of medical imaging data. So modality spanning chronoscopy, ultrasound, dermoscopy, CT, MRI, and microscopy. And we have found that our model is actually doing really great compared to all other methods. So if we see this plot here, we plotted in the x-axis we have the plops, that means the compute requirement, and in the y-axis we have the dice score, that is the overlap between the original image and the ground truth prediction by the expert. So, and here the bubble size in the plot represent, the bigger the model, the bigger bubble. So we need a smaller bubbles to have smaller models. And from this, we can see that our model actually lands in the top of the plot, having best dice score, while left and smaller bubbles means comparatively less compute and memory requirement than existing methods. And we evaluated our methods on different kind of hardware platforms as well, including mobile platform. And in case of mobile platform, it can process 35 frames per second in neural processing unit of the iPhone. So now I'd like to show a qualitative example, because segmentation, doctors usually use the qualitative outputs instead of using just dice score or segmentation results. So here is a real clinical sample from the colonoscopy imaging, and our goal is to segment the polyp here. So this is the polyp region, and if we see existing methods from the CNN-based, convolutional neural network-based, and transformer-based methods, we can see that they have false positive and false negative in different part of the image. So if we now provide this to the doctor and doctor try to use this to during the surgery to remove some part of the clone, they can actually remove some good part of the clone, thinking this is polyp, and they can keep some polyp that is called residual polyp, and that can become big cancerous. So, and our method helps reduce this significantly, and we have our methods results that significantly overlap with the original polyp region, and this is because our method is based on multi-scale convolutions that helps to focus on this polyp region very well, capturing different kind of context together. We also applied our method for ultrasound imaging here, and our target is here segmenting the breast tumor. And in this case, also existing methods, they have scattered false positive and false negative, and our method helps to reduce this significantly and produces better segmentation of the tumor region. Now, if I conclude this part, so we introduce a new efficient decoding architecture that is built on our new multi-scale depth-wise convolution operation that can capture rich context at low compute, and our decoder is a plug-and-play decoder. Here, plug-and-play means it can be used with any existing or forthcoming encoder architecture that is hierarchical. And in results, it can reduce the compute requirement around 80% compared to the existing baseline, and outperforms state-of-the-art methods access 12 datasets of 6 tasks. By this way, the key conclusion or key takeaway is the proper decoder redesign can advances the deployable healthcare AI in healthcare that is both efficient, both compute and memory efficient. So my next part of the presentation will focus on making this kind of architecture or any kind of U-shaped architecture reliable. So how can I actually make them reliable or generalizable better with the same compute and same amount of data? So I will talk about our new RIFs 2025 paper. So where we introduce a model that the goal is to improve the robustness and data efficiency with the same compute and same data. And we can see that like it can improve the rare and hard case segmentation accuracy. Accuracy means the dice score up to 20%. And let me talk about this contribution. So again, I'm going to cover the U-shaped architecture, but now I'll focus on the output space. So from the U-shaped or unit architecture or any U-shaped architecture, we can extract multi-scale information or output from different stages. So for example, here P1, P2, P3, and P4 having different scales, and it captures different kind of information, although it's the same forward pass. One is very high resolution and fine grained details, another is high level details. This fine level information are very useful for pixel level classification and segmentation of smaller thin objects or structures. However, the coarse informations are also useful to localize the object itself. So now if we see how does this actually optimize during the training phase. So when we actually optimize during the training phase, in most cases, existing methods use the final output, that is the fine grain output, during the training for supervision. They supervise only the final output. So this is called last layer supervision. In our case, we called it. And in other cases, there is also deep supervision method that actually optimizes all of these outputs together, but they are optimizing. They have two fundamental limitations. They consider all of this independently, that means in isolation with fixed weight. That means it can be constant same weight or a manually assigned weight. So, and it also cannot capture the complementary information across these different kind of scales like P1, P2, P3, and P4, how do they interact. So we try to come up with a better supervision method, and we come up with the idea of can we co-optimize this P1, P2, P3, and P4 in a way so that all actually becomes optimized toward P4. So P1 also be more reliable and more better segmentation like P4, although it's very coarse information. So yes, we come up with a new solution. So that is learnable logic mixing. So this is a supervision method again, and this is a plug and play method that we can use for any kind of task that uses U-shaped architecture. So here we come up with a new augmentation mechanism in output space. So people usually do augmentation or generation in the input space. For example, in this today's talk, some of the speaker also, Dan was talking about synthetic data generation. So generating data, that means input, and then fed to the network, and we train the model and we improve the model's performance. But here our goal is to keep the data same. We are not actually extending the data set, but can we improve the model's robustness or generalizability, introducing better supervision or regularization in the output space? Yes, we did that and we come up with a new method. So let's see how that works. So to do this, we come up with a new combinatorial synthesis module after when we just actually pass through the network, U-shaped network, and then we extract the different resolution output P1, P2, P3, and P4, and resized all of them to the target resolution. And then we send to our new module here. This module's purpose is to mix these outputs into using different operations like addition, concatenation, multiplication, and attention weighted fusion to generate synthetic logics. So this synthetic logic goal is to actually increase the diverse logics or information that model can actually get information from or get optimized. And yes, you can think this is like mixing local information with the global information, or mixing coarse information with the fine-grained details. And this way we are getting hybrid information that helps to improve the model's regularization and generalizability without using more data or more compute. Now, so this is actually helping to generate new information. But the question is, all of this information equally important? So by this way, so by this way we introduce, we actually send all of this information to the loss aggregation module um, during supervision. So, and we calculate the loss for all of them and we optimize the combined loss. So here from these 4 operations, we are getting 44 new synthetic logics. So 11 for each, because we are actually combining all of them using all of their combinations, 2 of them, 3 of them, and 4 of them together in this 4 output here. Now the question is, are all of this information or synthetic and original logics equally important? They may not equally important to the model itself during the training and different phase of the training. And to make it adaptive, we introduce a weight learning module where we assign each of these original and synthetic logics a single parametric value when we start the training process, and then we optimize this value with the model training, and that helps to actually emphasize which scale and which of these synthetic or original logics more important during the training phase. Across the training phase means like in early epochs or the later epochs, we can see different kind of waiting for different kind of operations and different kind of resolutions or outputs. And yeah, so this is very much effective, and this method we use for different kind of U-shaped architecture that I'll show now. So when we apply this method to different U-shaped architectures, including unit, attention unit, trans unit, Unext, and like our even recent method I just actually talked about, PBT MCAT, in all of these cases, our low mix helps to improve the model's performance without using more data or more compute requirements in the inference space. So this helps to improve up to 13.5% over the last layer supervision and 5.8% over deep supervision. And this gain is constructive gains because we get more gains when we have smaller organ or complex or hard organs. For example, right kidney, left kidney, gallbladder, and pancreas are getting more gain compared to organ like liver. Liver is a very large organ. It's actually getting gain, but the gain is comparatively lower gain than other organs. So this means that our method actually synthesize new logics that's helping this kind of rare organs or smaller organs. Model usually see less information for that, but we are providing more information and helping the model to generalize there. And our method is also highly data efficient. So when we evaluated our method for data efficiency by bringing like different kind of fraction of the data from the training set, for example, 40%, 20%, 10%, and 5% of the training data from the training set, we can see that when we have less data from the training set, our method is actually showing more gain compared to like if we use more data. So here we are using our like PBT MCAT, like our recent method. So in that case, that's already optimized method. Even after that, our method is actually further improving its performance just using better supervision method. And these gains also constructive gains again. So we are getting more gains in case of smaller, low contrast, and varying organs like stomach, pancreas, and gallbladder here. And if we show the segmentation quality, it will helps to actually visualize this correctly, like how this actually helping. So this is the 8 different organ segmentation in the abdomen CT scan. And if we see existing last layer supervision and deep supervision, that actually can segment some of the organs very well, but they struggle with here stomach and pancreas. For example, they have scattered false positive and false negative in different places. In case of last layer supervision, it is more, but in case of deep supervision, still there is some false positive and false negative. And our method helps to reduce this significantly and can do the better segmentation of the stomach and also the pancreas region. So this is because we are producing new logics in the output segmentation, and that helps to better regularize and generalize the model over different kind of organs better. So to conclude this part of my presentation, we introduce a learnable multi-scale generative supervision method, and this supervision method is plug and play. It can be used with any U-shaped architecture, and not only for segmentation, but we believe it can be used with other different kind of tasks that includes U-shaped architecture, like even generative modeling maybe. So, and this is highly data efficient with synthetic logic generation, and our method is improving more than 10 networks across 6 tasks, and we're getting up to 13.5% improvement in our evaluation, and small hard organs are getting more gain. By this way, the key takeaway is data efficiency and reliability can come from better supervision method. It does not always come from bigger model. So we can make the model bigger and bigger. That can improve the generalizability, but we can get the similar kind of generalizability using better supervision method. So in future, my goal is to advance the healthcare AI. So I can see like the use of different similar kind of strategy, like efficient architectural design, as well as data efficient and reliable learning method across other different kind of problems in hand. So for example, we can address the efficiency concern in multimodal healthcare area. Right now, most of this method focus on only vision task, but how can we extend this to multimodal domain? Then we can actually do generative targeted data expansion using this kind of multi-skill supervision method. And also we can make as I said, I didn't actually explore that part in my talk today, but we designed also method like robust adaptation of methods in medical domain foundational models. So how can we make the methods of self-therapy? That's another direction we can pursue, utilizing this kind of concept. And finally, as all of these actually focus on efficiency and making them reliable, so it can actually be used for real-time AI systems for emergency medical service or surgery, or where we have large scale data, like in the prior presentation by Professor Tolga Tasdijan, he mentioned about large scale pathology images, and in that case we can maybe use efficient method to actually encode large scale tiles there or images there. That would be also useful. Yeah, thank you everyone for being with me. I would like to also thank my collaborators, my advisor and mentors for guiding throughout the process. And yeah, I'd be happy to take question.